Okay, in the third question, we are asked to draw a motion diagram. So we're given this large space on which to draw the motion diagram. And as we read the question, a speed skater maintains a constant speed clockwise around an oval track. So here's our oval track. We're going clockwise around that at constant speed. So let's highlight that. The circular ends of the track have a radius of 8 meters. So they go in toward the circle and are joined by a length of straight sections. Draw a motion diagram for the skater. On your diagram, label the velocity vectors and the acceleration vectors. So to start out with, we know we're at constant speed, so we should be putting dots equally separated in space around our motion diagram. So if that's our initial distance between two dots, we'll try to maintain that same distance as we go around our motion diagram. So we start out by putting a number of dots around our motion diagram. That one was a little bit too close. These should be equally spaced dots because it's constant speed. So we've gone all the way around. We're going around clockwise. Clockwise is this way, sorry. So clockwise, we draw straight line arrows that join the points. Vectors are always straight lines. These straight line arrows represent the average velocity between these time intervals. So we're almost all the way around. Okay, so we've got clockwise. These are velocity vectors. Now you could use one color for one type of velocity vector, for one type of vector, and just say, okay, this is a velocity vector, but I'm going to be using the same pen, so I'll label every single one of these vectors. And now we want to also on our diagram label acceleration vectors. Well, in the middle, there's no change in the velocity vectors in the flat section. So our velocity vector would be just a dot. Our acceleration vector would be just a dot in the flat sections. And in the circular sections, it's not going to be just a dot. Here we see that there's a slight downturn in this vector relative to that one, so there'll be a tiny little acceleration vector roughly towards the center of the circle. And here there's a bigger acceleration vector towards the center of the circle. As we go around this circle, this is circular motion. And so at every point, there's an acceleration vector that corresponds to the change in the velocity vector pointing towards the center of the circle. Each of them gets a label of acceleration. And then we do the same thing on the other side. Tiny tiny and larger acceleration vectors. All right, now, so we've finished our motion diagram. We want to find the acceleration of the skater at point A. Point A, acceleration is a vector. So acceleration vector has a magnitude, v squared over the radius. This is in a circular motion, centripetal acceleration. And in this case at point A, we know it's pointing to the left, or some might say to the west, if this was north up. So let's put in our value of 10 squared, divide that by 8, and this will be in meters per second squared since this is both in SI units. And 100 divided by 8 gives us 12.5.